I hope staffs are there so everyone can understand. So, so hesitate to ask in Assamese, Assamia, তেনেকৈ আহক. Just if you have questions, English di কৰিব লাগিব, nothing like that. Okay. So, yeah. So, this is as sir and my friends and the faculty have already mentioned, is under secret of the universe through the world largest particle accelerator, LAC, Large Hadron Collider. So these are the brief outlines. So let me try to give an impression of each topic, what we will going to learn or deliver for today's talk. First is introductions, where I will try to give the background of sorry study and what I'm doing and what the peoples are doing all over the world. So and what is anyone can have. So the full form we know that it's a large hadron collider. Then the next questions is the hadron collider, right? So and then we have, I think someone is unmuted. So what are the different discoveries that we have from the LHC till now? And that is for all, I would say. So it's not that this LHC is made for only this specific technology is applicable to the general public, and it is actually it's being used different areas. So the societal impact, and the last part is the future of LAC. That is when I'm saying future, it could be like 50 or 100 years. So I will try to describe about the future. Okay, as an introduction, so I would like to start with which sure which all of you must have during the school days or maybe before that. So we are all curious as a human being. So we minds is fascinated to like understand the surroundings, right? So I was very interested, and I'm sure the other is the same. So was interested with questions. So what are the principles that governs the energy, matter, space, time, and what is this world made up of, which we can see from our naked eyes? Stuff that we can see, science can give us more insight, which we cannot see. We can just see through our right. So and finally, how does it work? That's the our job to understand as a physicist. How does working like this way? Okay, so well, the high energy physics tries to answer this elementary levels, but it's not that only high energy physics can give these answers of these questions. Different branches of physics, the science sides can give the answers of such type of fundamental questions in their own. So I will be, because I am belong to a very specific branch of physics, which is called high energy. My talk will be like towards the high energy physics, what are the culture, and what are the how we try to discover or can give the answers of these questions from the high energy point of view. Okay, so high energy. The first question is that why high energy? So because we have already the uh, which is like nowadays when I was a undergrad student that time it was very popular. So so I was wondering the high energy. What about the low energy and what is actually the high energy is? So the with the minimal equations. So the high energy, why we call it high energy? Because we have already the nuclear physics. Okay, the nuclear physics is considered to be the low energy physics. There is no such things as high or low. It's just the energy ranks. So we can we name in like this way. So when we say talk about this MEV range, that is the mega electron volt, we physics domain, which is the we can go up to the nucleus. Okay, I will not discuss about that part. If you want to go inside the nucleus and precisely the inside the nucleons, that is the protons and the neutrons. So that amount of energy. Why? Because there is a fundamental principles that the probe wavelength as problems we are going to inside of something that wavelength should be smaller than the distance scale to you are going to probe inside the nucleus. So your energy accordingly will be higher. This principle actually governed by this we can describe that. It's just the simple form of this equation, which is the lambda is proportional E. The proportional for the undergrad student. I think you must know, like you have you the equations which tells us that this p is the momentum and lambda is the wavelength. So you can easily transfer the momentum into the energy. So you can see that it is a lambda and the p is inversely proportional. If you just go smaller and smaller, that means that your lambda is smaller and smaller, then your energy should be higher and higher. Principle or that's the fundamental rule. So if you just want to go deeper into the nucleus, that means you the values h, by the way, h is the Planck's constant. It's a fundamental constant, like the gravitational constant we know all from the Newton's law. For the elementary particle physics, we have a famous constant which is called Planck's constant. So if you put all the values and everything, so you G value is of GeV, that is a giga electron volt. And from there, we consider it to be a high energy. Okay, we have much than that. We are now in the tera electron volt, which is approximately like 10 to the 12 electron volt. Okay. So now going to the next slide. So how we can prove the before that? So we have this that in the lab most we have the macroscopic buildings, including us inside the building. So if you just from theoretical perspective, if you just let's say we have something by what we can go see or we can zoom these microscopic objects. We have the telescope, right? Telescope, not telescope, it's a microscope. So if we can see the details, so we can see the sand and the stones of the building. And if you have more sophisticated microscope, let's say, you can maybe you can see the crystals inside the stones. And if you have more sophisticated thing, then you can go like further into the crystals, and then you will be able to understand, or you can maybe atoms. I'm not saying you will able to see in the naked eye, but can like have an idea that yeah, that must be an atom. So you can see the range about which you have to like zoom in. Then if you yes, passionate to know, so you can go inside the atom. So you see, if you go inside the atom, there are so-called nucleus, and there are electrons which are revolving around the nucleus. So nucleus is like not a 12 centimeter. This is so microscopic, right? So we are already in a domain of atom that is not visible yet. Now the story begins from here. Like my study and we people as our domain of study starts somewhat after the nucleus. So if you go beyond the nucleus, if you just go beyond the nucleus, you will see something called that is the protons and the neutrons. And from modern day wisdom, modern day techniques and everything, so we know that this protons and neutrons are in the subatomic level, so which is made up of quarks. Uh, as you can see in the rightmost, Einstein called it quarks. It's a there because there is a specific colors. That's a very important thing. So because quarks have some colors, as is the fundamental colors. So now, from our current understanding and the development of science experimentally, so we know that these quarks are the building blocks of atoms. Not the science is evolving, and with the recent technology, we can be like go further with quarks. Uh, and till now, from our current knowledge, we have the six quarks. First is then down, then the strange, then charm, the top and the bottom. So there are everything is verified till date. So there is nothing like it's not a theory. It's now we believe that there are six quarks, and we have to deal with it. We are left with these six quarks. The one thing it's very interesting that it's not a free particles like protons and neutrons. It can be only inside the protons and the neutrons. Okay, so the protons are made up of up down, up and down quarks. The combination of because there must be similarly up and down quarks only. So then there are other quarks. So there are the up and down quarks are lightest, and the top and the bottom are the heavier quarks. Okay, so as the Shikha man told my talk, this is a heavy flavor domain. So we call it the up, down, and the strange is a light quarks, and the charm top and bottom are the heavy quarks because their masses are heavy. Okay, and they have the fractional charge. So you must have seen in a textbook that we should not have any fractional charge, but that is actually the free fractional charge. That is, you will not get this quarks. You will not get this quarks free ever. So that's it has the fractional charge to make the proton charge, let's say plus one plus like plus charge. Okay, so now, so we know that if is elementary level science, so you know that these atoms, we know atoms. Now the question is how to inside the atom we can experimentally verify that yes, there is something like works, and we can even further study the domain or how the quark behaves in that domain. So that's why this cartoon. So you see the atom, which is a big atom, let's say. So the one thing you can say, like you should have the microscope, the resolution should be high that you can just go inside the atoms, the nucleus, then protons, and unfortunately, we do not have that much technology yet. to make a microscope and can just diagnose the atoms and can go inside the atom. Is we know that somehow to know the building blocks of matter of something, you can just destroy matter, and you can just if you just smash the object, and you can get the pieces of it, trace back by reverse engineering. You can have some idea that okay, so it is made up of this. The idea we we cannot go inside the atoms in easier way. So what we do, we collide the two atoms say the nucleus, let's say atoms or nucleus. So because we can ionize the atoms and we get the nucleus. So we then this from this nucleus, then it's that the it needs the tremendous amount of velocity just collide. Just collisions will not like melt down the atoms or melt down the nucleus. You just need so much energy when the atoms collide, it just melt down or it can smashed and it can form something out of it. Like so that's the idea behind it. So we can collide. But the thing is now some instrumental thing, right? So what's the instrument? So then this is the talking about, which is called LAC. So it is a Large Hadron Collider. It is called actually the tunnel. This is called the Large Hadron Collider, which is situated at the French and the Swiss border, the French side, and the half part is in the Switzerland side, basically. Okay, so and the organization that is the Large Hadron Collider is the name of the ring. Okay, uh, I will talk about the organization that is an European organization which is called CERN. So CERN, what's the full form of CERN? Actually, that is coming from the letter slide. But for us, for the English people, so it is uh, a European organization. Okay. So what is this? So this is you see from the like it's a from the above. So you see here, it's a long tunnel kind of thing. So you can see a picture of tunnel inside it and one video to visualize what it is actually. So there is a long tunnel of 27 kilometers. Yeah, you see there are four names here. So one is there are actually these where the collision happens. So here inside the ring, what we do, we mainly now we collide proton. We consider it's a small system. So proton made up of three quarks. If you just can have some out of it. And if you just imagine the lead, which is a consist of I think atomic number 82. So photons are just accelerating inside the tunnel, and you can just collide it, and you will have something extra. That is actually my domain, which is called heavy ions. The lead here, the lead is called the heavy ion, and the proton is called the uh, small system. So here you are seeing the 4 points. It is in the one is the main building is. So one is the ALICE, and one is the CMS and the LACP. So four detectors, and eventually it's the four collision point where the collision actually happens, and there is a detector. Detectors. So I am associated with the CMS detector, which is the compact muon solenoid detector. Okay, so the CMS and I think all these detectors are in the Switzerland side. Okay, so time machine because we can create the uh, that phase of matter in this ring, especially we can say here the Big Bang machine. Why it is called Big Bang machine? Because that a state of matter. Sorry, where we can study that of the universe just after the Big Bang. It's not equal to zero, but just after the Big Bang, there is a state where no matter was there, just an soup of quarks and the gluons were there. So quarks I have already mentioned are the nucleus, and the gluons are the, you can say, glue to combine it inside the protons. Okay, in scientific term, but that's it. So that was the matter. After that, the protons form various forms, then atoms, then we can go reverse way. Okay, so that's the Large Hadron Collider, and I will many facts about the Large Hadron Collider, how it is situated, what are the stuffs. So this is overall the Large Hadron Collider. I mentioned all these things already. So okay, so going to the next slide. Sorry. Yeah. So coming to the four collision points, I have already mentioned. So there are four collision points. The four collision points, there are four detectors because we are interested in uh, the particles out of collisions. When the collision happens, you imagine like that way. Suppose the protons collide, so what happens? The individual identity get lost. It's no longer the proton, okay? Because the energy is so high. There is a high electron fault right now here in this LHC because we have some low energy like a few GeV and we can have such scenario, but the energy that LHC have is much more bigger, and it's the highest energy world have right now. So that's why. So when it collides, it's just get like smashed, and it has no identity. So in the collision points, there are many things that happen. So those four collision points are the four detectors. So one is the Atlas I have mentioned, and one is CMS, one is ALICE, one is LACP. So I am associated with CMS. So general purpose detector. That means you can study everything, literally everything. So it was the first two detectors which was like proposed to have, and the right side too, that is the ALICE, ALICE, which is Accelerator experiment. So that is basically actually dedicated to the heavy ion physics. That is a late. They are more interested in study the those study in the CMS where I'm also working. So and the last one, dedicated one, it is made for the beauty physics that I have already mentioned. The beauty quarks in beauty. So that's why they have the dedicated detector. I also am not expert on that. So they have their own detector. There are lots you can study and you can just importance. That's why they have the special detectors. Okay. So that one is very general purpose, and I'm working on CMS. So here I go. Okay. So something about collaboration. IITM, as I have mentioned, for its European organizations for nuclear research. So the here it's in French, it's Council European for La Research Nuclear, something like that. So from where the sun come from. So the all the data is up to 2020, 16. Okay, so 2010, so there were 22 member states. Okay, you see, so to build such a collider or such a collider requires so much money. In fact, yeah, that's the first reason. It is not that we can build in our lab, or even it's not possible even for a country to have not only just building the machine to work and the expenditure that to operate this machine. That's why we need. There is a signature you can see here in the left side. There were 22 member states and 12 European countries were there. The the concept of having such kind of collider is very long back. You can see here 1954, and the budget was around 10 to the power 9 CHF with approximately 900 crore for in Indian money. So there are several signatures here for all the ambassador or the government signatures are there. It's very important page that I collected from the internet. So that's not all. So we are interested in where India lies, right? So about so the CERN collaborations. So so to have such a collider and such a collaboration, there are so many countries and so many peoples are there. So and everyone, everyone is using CERN in some or other way. But there are some members who are more associated. That means they are partner, like those are called the member or observers. So, and then there are associated members, there are some other called yeah, mainly these two member states. One is called, another is associated members. So India was like associated member in 2017, this data. So here you can see here this from India. From India, there are at that time there was 336 I think people, but it's much more bigger. I would say almost 10 times bigger now. So the all the members, all these engineers, all the people, PhD students, there are postdoc students are doing. So here it's the day. I remember the exact date, but it's the Indian ambassador, I think Amardeep Singh, and signed the membership with the CERN Director General. She is the Director General, and here is the statue that is Thanatras from the DS Department of Science and Technology from India, and uh, there is this statue. Famous statue is there. It's very nice to have this statue in this such a uh, like big collaborations. Yeah. Okay. The CERN collaborations. I know you can get in the internet. You can get a lot of stuff, more stuffs if you are interested. But one is the biggest collaborations in science, if I'm not wrong. So because there are so many members to push the boundaries of science. So it's the fun I have included because there were some rumors when it was just situated, like when it was just established. When I used to study, so there were first time that LHC operated at I think 2010. So there were some news in the news. There were some news that is world get destroyed and everything. mini black hole in the Earth, and there will be so much radiations. What about these radiations? If they can harm the people, and the magnetic field. I have not mentioned about the magnetic field. There are a large magnetic field around 4 Tesla is used to the magnetic field can bend the charged particles when it moves. The magnetic field, the field bends according to their charges, right? So they can bend and in the accelerator. So we need a dipolar magnet is used, and those magnetic field, if I'm not wrong, so that is the highest magnetic field used in the machine. That is a 4 Tesla, it's a huge magnetic field. So there were this type of questions. So here we can want to say that the energy is not harmful at all for us. We can see the calculation. So the red lead collisions is much more lesser energy, but proton have the much more higher energy. So if we assume the highest energy of the particles, so now we have, let's say, 14 TeV, tera electron volt energy, and it can be achieved when raised center of mass energy is 10 to the power 5 TeV. It's a little bit technical, but I think you know your physics, so you know the center of mass energy. So and because it's, you see, the center of mass energy is can calculate here, and this energy of proton, you see 10 to the power 5 TeV. Then the primary cosmic rays, which is like uh, the cosmic rays at all the time showering above us from the outer space. So it has the energy which is greater than the energy of the particles. So you see here the energy is 10 to the power 8 tera electron volt, which gives the center of mass energy much more greater than the so when we say the energy of the LHC, we only talk about the center of mass energy. So all this calculation means that to have this center of mass energy, what is the energy of the particle you should have? Okay, so that is the calculation. So you see the protons should have the energy is 10 to the power 5 TeV, but we have already the cosmic rays which have the energy 10 to the power 8 TeV. So if we can just survive those energy, it's not that harmful, I guess. So, and there are even more energetic collisions are going on. Who knows the, because I'm talking about the very small thing. Who knows about the big black holes and the outer galaxies? There are even more energetic collisions are going on. So the final point is LHC collision is not going to end the world, or it is safe. Okay, so it, so after having all this, so let's have a look on how actually collision happens. It's the visual effects, so you can have. So let's, it's a short video. You can just see here how it works. So you see here is the ring. It's not so many stuffs are going on before actually the takes place the collisions. There are some detectors are there. This is the LHC ring, and this is the proton. Okay, so because there are, you see there are three colored box, and it is the one detector which is at last the simulation view. So when the collision happens, just you see there are this all the this we call it tracks. These individual tracks are referred to as the can see on particles. So there are a lot of particles produced from that collision, and we need to identify those particles. Okay, so this is the view. I hope the picture, at least the mental picture, is clear. And we can have all this data. Now, this is the one part. Now we collide, and then and we will have the data. Okay. So to analyze the data is the our task. So that mainly we do the researcher do to analyze the data, but it's not that it's there are so many peoples are there to get the data into our access. So there are people who protons, blades, and then there are so many engineers who built this machine, and there are technical staffs. So we have to consider all of them because without them we cannot do this research. Okay, so that's why this means like okay, if this much is clear, can I have like
Yeah, yeah, sure.
okay, so I'm
Okay, you
in the
have 10
middle,
minutes.
so that's why I'm qual like this is a small question. So okay, so here in this slide, I mentioned there are some events, important events which LHC had during the previous years. Here, the same form I because the LHC histories are even further beyond the 94. I have included from 94, and the concept and everything. It is like more than I think 19, just after the 1950s, around 1960. And after that, there is long years to have all this collaboration, all these countries together, meeting, stuff, and everything were there. And after that, so there are the historic events which LHC have. I will try to mention one by one if I have time. Yeah. Okay. So already it's 4:40. Okay. So there are 16 December 1994, the construction approved. Then after that, 95 report published. Then this 97 in 97, the first the CMS and Atlas experiments approved. Then this actually that was the general mentioned. Then after that, this two special kind of detectors that is in ALICE and LHCb was happened like in 1997 and 1998. Okay, and then the 2008. So after this long years after building, so in 2008, LHC actually just after the starts, there were some technical problems. Then again, it get stopped. From 2010, it is the 30 March, the first LHC collision happened at 70. This is the date actually where all the media people and we got to know like yeah, there is on there is some stuff. So then in 2012 we record the high is in 8 TV. So in 2010 I was in class 10 and 2012 I was in class 12. So that time didn't imagine that I would be working here. So this is 10 years down the line. So after that, 2012, what happens? So you see CMS and the Atlas observe particle consistent with his. I will later talk on this. So what is his version and why it is so important? Why it is mentioned in the later slide. So in 2013, so end of LHC run one. So actually, what happened is this happened for a few years, let's say 2 to 3 years. Then after that, LHC upgrades. Okay, so you see after 15 years, so then again for 2014, actually gears up, but actually from 2015, the more two was happened, and in between there was a event 2013. The Nobel Prize for this Higgs discovery was given during this long shutdown. So in 2014, this LHC gears up for round two, and this 15, this is the beyond like 13 TeV happened, and in 2022, from 6 July, it's very recent. I was concerned. So LIC gears up for run three and achieved record energy of 13.6 TeV. That is the energy what so that is the highest energy we have right now. So on 18 November 2022, so LHG achieved record energy because there are two kind of collisions. One is PP, one is late late. So 5.36 TeV because I am working on maybe late late, so it is of my interest. That's it. So there are different research areas. So I have included few of them here because stuff. Now research areas. So there you see this LIC is a multi-purpose. It is made for let's say next 100 years. Okay, there are several branches of physics, I would say. So there is Big Bang, where I am working on. It's the one word, but there are a lot of people are working on this area. There are the extra dimensions. If you know these string theories, people like playing, there should be some extra dimensions. So those studies are also going on. There are one concepts called dark matter and dark energy, which is like very like interesting. It used to be like in astrophysics stuff. Now we have in particle physics this dark matter and dark energy, and also I guess uh, yeah, Devabrata's work is also like in between this dark energy and the standard model physics and beyond. This standard model is like right till now we have the satisfactory model which can explain the behavior of all the particles, all the subatomic particles. Yeah, as it is a satisfactory, not the ultimate model. We have the signature, but its model is not the ultimate model. We need to go further. So there are new physics, some kind of already we are having some signature. That is not all. We have the like beyond the standard model. There are some physics which are still like not explained in the theory. Keep the vacant place because from LHC collision we don't know what is coming. So there are always the room for new stuff. That's it for all this research area. So I am mainly working on this Big Bang part, I would say. So particularly in quark, gluon, plasma. So next slide is these are the modern questions. I mentioned in the first slide, those are the philosophical questions, scientific questions that we have right now. So what is the origin of mass? That is a mass that we can see that every object around us has mass. So where this mass coming from? And this will we discover the evidence for supersymmetry. The supersymmetry is a theory, like exotic theory, so which tells us that this fermions and the bosons, if I'm not wrong, you know this are half integral spins and the bosons are integer spins 0, 1, 2. Okay, so those are the are partners of each other, but till now we do not have any signature of that. But there is people are still working on. And then there is the dark energy, the matter energy, two different things. So this is one bold questions is there. Why is there not more than antimatter in the universe? I think Davidov is an expert on this topic. So his studies lies in this to answer this question. So, and how does the quark-gluon plasma give rise to the particles that will constitute the matter of our universe? That is my area of research. So, okay, so this is what we have till now, and these are just a question, not just a question, but that's the whole lot of like areas of research. So there are thousands of people are working in each questions to answer the questions. Okay, so I will mention this end part of the talk. So there are a few discoveries I should mention before ending the talk. So there are two rounds, right? So there are first round there happened to be from 2009 to 2013, and there are the discoveries list. So I will not mention one by one. I should mention few of them. Let's say 2021, Alice reported the formation of this quark gluon plasma, which is very like a visual state. So this state is supposed to be existed in the beginning of our universe. So after the Big Bang, just few milliseconds after the Big Bang, this was a state, and we can have this state in the laboratory. We actually have this. I am just like studying the properties more quantitatively of this quark-gluon plasma. And I mentioned the Higgs, right? So the Higgs was the last masterpiece of the standard model. So that is, you must have heard of the God particle. So that is called the God particle because this is the particle which is responsible for the mass of the particle. So to discovery and to explain how we actually have this particle is a long journey. Because in 2011, Sun reported that the standard model Higgs boson, if it exists at the time which they were given, it should be from 1152 to 130 GeV, and then later the two detectors from its existence. So detectors have also shown intense peak in 124 to 25 GeV. I will talk about that just few slides later. So on 2011, there were some particles, new particle, composite particles emerged, and in 2005 and in 2012, both CMS and Atlas announced the discovery of these Higgs bosons. Okay, and then in 2013, CERN actually announced the confirmations of these Higgs bosons. You can see the video in the YouTube. So in August, there were two particles called B emissions decays, and it indicates that the standard model is not the end of the story. There are beyond that. So two other the LHC B. So observe some multiple exotic hadrons. That means right now we know that particle consist of either two or the three quarks. Two quarks, that is a meson, like I studied like DS. There is two mesons, and like quarks, it is called hadrons. Okay, so but there are evidences. There are some particles which consist of more than three quarks, and actually that theory, if there is more than three quarks, then the theory will change. The physics will change. Physics needs some modification. So that's why I'm studying that. And in the second run, there are mainly all these studies because this is very we need a lot of studies. So many studies were done to increase the precision, and there were several new particles which were discovered in this run because now then we had a lot of more statistics. Actually, I am also studying the run 2 studies, run 2 data 2015 to 2018. So you see here, there again, there are a lot of particles that were detected in this run. This is called hard run, which is like started from the 5th July and it's still ongoing. It will go at least for 2 years, I guess. So now these experiments have discovered the 59 new hadrons in the data collected during the first two runs. Okay, so we have the 15 new particles and still counting. Okay, now the thing is, this is so much exciting or fascinating for me, but how do we actually work? That's the main question. So, as I have already mentioned, there are so many people. So I have this chart of workflow to like explain how we work actually. If like to have an idea, because ideally you can work for any corner of the world. Like it's such a network, so you can you need a laptop, you can work from there. So you see, first is getting the proton and the lead ions. There are dedicated stuff. They get all this stuff. Then after that, you see the ring there where the collision happens. Then one task, one is called data processing, because this data is not just that a small amount of data. This data is high-fi computing skills or computing stuff. So there are lot of brilliant brains of engineers are there. So to process and make this data analyzable. So we call it this data is AOD, which is the analysis objective data. This data itself is a huge size. We need like a few terabytes. Like to accommodate all the data, you need I just is a very less in the context of data. So we just squeeze the data in the form of sometimes I'm using MiniOD. So still I need some terabyte of space for that data and to process those data. So from here, one PhD student or the researcher like starts working. So you have to have this computing account. In the cluster, we work in the cluster. So you have the computing account. You have to like then in the after getting the computing account, you have to pause and work. And then after our works, like all everything is computational, and we use mainly Python programming. And you must be knowing like everything, all the researches nowadays are shifted to computing because data is very important. Uh, so then after if you have the analysis framework done, then you can just run the data so that you have all the access of the data. One thing to mention, so this data of that LSC produce, it's not accessible to all. You this this institutional registrations, then only you can access the data. So that's why we have all these and all that. So after that, you submit the job in the grid computing system. That is also one big area of that is actually, I would say, they discovered itself in the sun. So grid computing is kind of you can use large computers. You can just use all this computer at once. So I can use, let's say, somewhere in MIT or Oxford or let's say in other part of the world, if they have some computers, I can use from here. That's what like in layman language, a grid computing is. I submit the job and it will run anywhere in the world where the this space is available. Then you need to store this data, like the output of my result. So we have one cluster in the PIFR Mumbai, Tata Institute of Fundamental Research Mumbai, and that is also they have the dedicated work force to like maintain those stuff. And after that, and everything, we need to have this approval from the collaborations because no results could be published without the approval of collaborations. There is rigorous method, like rigorous base that we should approve they have already. Then after that, we go to the publishers to publish that. Then again, we have this few questions or reviewers comments that everyone do, all the other researchers do. Then we can say that yes, we can say that we have a discovery. So there's a long process. So I have bracketed this down. These are the works that we or whatever the researcher do all the time here in computer. So now, so when we say how it looks like, so for us, so this is the particles looks like. So you see here the left side, this is partitioned that, so there is in 125 to 24 to 25, there is a small peak, you see, little peak. But in the curve, you can see there is a some method to estimate that yes, there is something that energy range. I'm saying energy is the mass because in this area, so mass and energy is the same thing we consider. So here is particle, this looks like this, and the middle one, this you can see the phi particles, which actually is also the particles, particles, but this is from the CNS that I'm working on. This is the phi particles looks like, and this is one from the LACB. You can see the large peak, right? So, and the last one, this is the my particle that so this is the D sub S. So D sub S is essentially it's the combination of it's a particle which that's why it's called meson. One is charmed and one is strange quark. Okay, so we got these particles here. This state. That's why I need to put the logo. So it's in process. Sorry. Okay. So this is the particle. There are lots of particles everywhere. If you search some particles, you will get some curve like this. So then only for particle physics, means to have this graph, to have this plot. Okay. So now the last part, which is the actually crossed my time. So actually, okay. So
Yeah,
this
I
is the
think we
application
should
part.
summarize quickly.
Yeah,
Yeah.
yeah. This is the actually application. So the applications part. So I have mentioned all the links. Maybe I could share the slide, and if you are interested. So the one thing that I should say, so this World Wide Web, so which is now commonly we say computer, so internet today, was discovered in CERN, or and it is connected with the Greek computing system. And you see the picture in the rightmost bottom corner. It's the corridor was discovered. So this is the there are like its technology is used in the satellites and some aviation industry as well. So you can just click and search. And I have given the source also. If you are interested, you can just go through it. Yeah, it's the future. I should mention like whatever I am the LAC. So the future is even much more bigger. So the future collider would be around 100 kilometers, let's say 3 times bigger than the present LAC. That's the idea. And yeah, that is for sure. We are not to witness this. So, but it's the, let's say it will take more than 30, 40 years, let's say 50 years. But this is a huge thing I think we should have uh, and that's my reading slide, and that is actually summarize everything we we uh, we collider as a microscope to see in the atomic domains, and but most of the time we sit computer and try to like find out something, and most of the time we have to like solve the errors and everything. That's why this cartoon. And the left image is like uh, I was like got the opportunity to visit once during the that's the picture. So I was there. So, yeah. Thank you. If you have any questions, please the floor ask.
So thank you, Nihar, for the nice talk.
question. We have the question answer session. So there is a
Sorry
mono
for the
question
late.
আছে সুধিব পাৰা. The question can be
Yes.
very basic. Yeah.
Yeah. একদম বেসিক্স এক্সপ্লেইন কৰিছো, তো তোমালোকৰ যদি কোনো আউট অফ কিউৰিয়সিটিৰ কোনো কোৱেশ্চনছ থাকে ইউ কেন আস্ক। আই হোপ বেছি দেৰি অলপ দেৰি হৈছে বাৰু, সৰি ফৰ দ্যাট।
10 minutes.
Yeah.
Actually, we had a large number of registration, but the attendance is low. And
এইটো
I
হয়,
came to
তেনেকুৱা
know
হয় বাৰু।
that tomorrow these PG students have slate examination. So lots of PG students in universities and colleges, but because of this late examination, people are moving from here and there, so the attendance is quite low.
But yeah, it is too
মই এটা
grateful
সুধিছোঁ,
for me. Yeah.
প্ৰথমতে থেংক ইউ ফৰ
Thank
মিষ্টাৰ নিহাৰ দাস, নিহাৰ সাহা। আচলতে মই নিজেও LIC অলপ কৰিছোঁ 2008 to প্ৰায় 12-13লৈকে আছিলোঁ। এই চাইছিলোঁ আৰু কিছুমান বস্তু মানে ফিল্ড চেঞ্জ কৰাৰ কাৰণে কিছুমান বস্তু মানে ট্ৰেকৰ বাহিৰত গুচি গৈছে। এনেই ধৰক আমি যিটো হিগছ বজন মানে পাম বুলি এক্সপেক্ট কৰা হৈছিলে, লটছ অফ ৰিজাল্টছ ইতিমধ্যে প্ৰেজেণ্টেশ্যনত কিছুমান উল্লেখ কৰা হৈছে। তাৰে মানে নহয় আৰু মানে কেনেকা আমি যিবিলাক প্ৰশ্নৰ উত্তৰ আমি পাম বুলি ভাবিছিলোঁ, এই ইমান ডাঙৰ প্ৰজেক্ট বহুত কাণ্ট্ৰি বহুত ফাণ্ড জড়িত হৈ আছে। এতিয়া মানে সেই প্ৰশ্নবিলাকৰ আমি কিমান দূৰ সফল হৈছোঁ তাৰমানে এতিয়ালৈকে। Are quark fundamentals particles or made of something smaller yet? Why universe is what is the nature of dark matter and dark energy? এইবিলাক হিগছ বজন পালে মানে পালে আমি বহুত
নহয়, তেনেকুৱা ঠিক নহয়। মানে হিগছ বসনটো এটা এনেকুৱা এটা পাৰ্টিকল আছিলে, কাৰণ এই যে ফাণ্ডামেণ্টেল পাৰ্টিকল বিলাকৰ মাছটো ক'ৰ পৰা আহিছে, চ' সেইটো এটা কুৱেশ্যন আছিলে। চ' সেইটো এটা এড্ৰেছ হৈছে। বাট হিগছে হ'ব পাৰে কিছুমান ষ্টাডিজ এতিয়া হ'ব পাৰে, বাট এভৰিথিং গোটেইখিনি ষ্টাডিজ বিলাক যে কৰিছে, বাট কিছুমান ষ্টাডিজ আছে যে তেনেকুৱা ডাৰ্ক মেটাৰ is expanding, dark matter বা dark energy. So এই ধৰণৰ যেনেকুৱা টু ওয়েজ কৰা যায়, এটা হৈছে এষ্ট্ৰফিজিকেল পইণ্ট অফ ভিউ, তো পাৰ্টিকল ফিজিক্স পইণ্ট অফ ভিউ পৰা যোনটো কৰি আছে, ট্ৰাইং টু ফাইণ্ড সাম পাৰ্টিকলছ, কিন্তু এতিয়ালৈকে যিমান বিলাক মানে তেনেকুৱা কোনো পাৰ্টিকল পোৱা যোৱা, what is the status? The status is ongoing, the in process. এনেকুৱা নহয় যে কোনো এটা কনক্লুজন। হিগছটো এটা বিগ ডিল আছিল, সেইটো পোৱা গৈছে। মানে একচুৱেলি হয় কি, চ' এনেকুৱা কোলাবৰেশ্যনত 10 বছৰটোও এটা মানে সৰু সময়, নিড টাইম। চ' তেনেকুৱা ক্ষেত্ৰত কি হয় আমি ক'ব নোৱাৰো। আজিৰ পৰা হয়তো আপুনি যিবিলাক কুৱেশ্যনছ কৰিলে, আজিৰ পৰা হয়তো 10-20 বছৰ, 10 বহুত সৰু সময়, মেবি 50 years পিছত হয়তো আৰু মোৰ প্ৰিচাইজলি ক'ব পাৰিম। এতিয়ালৈকে যিমানবোৰ ষ্টাডি মই ইমান এক্সপাৰ্ট নহয়, হয়। হিগছ বসনছ যোনটো এটাতো মাছ আছে, প্লাছ হিগছ বসনছ একচুৱেলি বহুত বিলাক বস্তু ভেৰিফাই কৰে। এই যে ষ্টেণ্ডাৰ্ড মডেলটো, তো ষ্টেণ্ডাৰ্ড মডেলটো একচুৱেলি সঁচা হয় বা যদি হয়, ইমান এটা সেই আছিলে, তো সেইটো এই হিগছ বসনটো পোৱাৰ পিছত একেবাৰে কনফাৰ্ম হৈ গ'ল যে model that we have. So আমি সেইটো লৈ মানে like that is the model you can have, or is the biggest like achievement যেটো LHC আমাক দিছে। কিন্তু তাৰ পিছত দেখা গৈছে যে ষ্টেণ্ডাৰ্ড মডেলটো আল্টিমেট নহয়। সায়েন্স তেনেকৈয়ে আগবাঢ়ে। তো এনেকুৱা নহয় যে আমি সকলোবিলাক বস্তু পাই যাম। চ' ময়ে হয়তো মোক নিজকে কৰি আছো, হয়তো 10 বছৰ পিছত সেইটোৱে ৰং প্ৰুভ কৰিব পাৰিম। তেনেকুৱাই আগবাঢ়ি গৈ আছে।
LHC dark matter search is still going. So in terms of some missing energy,
কোনো
but they are still looking into this. Yes.
Actually, from neutrino perspective, there are some beams particles. Actually, কি কৰি আছে? Like scholar হতে কথা পাতিছিলো, ইণ্ডিয়াতে বহুত জনে কৰি আছে। সো তেনেকুৱা কি হয়, তেওঁলোকে এটা লিমিট সেট কৰি আছে যে য'ত মানে প্ৰথম পাৰ্টিকুলাৰ ডিসকভাৰ কৰাৰ আগত লিমিটটো খুব ইম্পৰ্টেণ্ট, যে এনেকুৱা লিমিটৰ ভিতৰতে থাকিব লাগিব। তাৰপিছত বহুত কনষ্ট্ৰেইন আহি যায়, বিকজ আছে আমি পাব নোৱাৰো, মানে আমাৰ বহুত বেছি ষ্টেটিষ্টিক্স থাকে। সেইকাৰণে নেক্সট টাৰ্ম যোনটো হ'ব সেইটোক LHC হাই লুমিনিচিটি হ'ব মানে। তো সেইটো আই থিংক 2024 পিছত হ'ব চাগে। চ' নেক্সট 10 years লৈ পিছত আৰু কি আই ডোন্ট নো, কিন্তু
যিটো মানে
কি চলি আছে
ইয়াতকে ডাঙৰ যিটো মানে প্ৰজেক্ট চলি আছে এইটো কেতিয়া মানে
স্টাৰ্টিং পইণ্টটো মই এতিয়া নাজানো, বাট আই থিংক এতিয়াও খুবেই প্ৰিলিমিনাৰী, লাইক কনচেপচুৱেল ষ্টেজত আছে, মানে ভবা হৈ আছে।
বেছি এৰিয়া কভাৰ কৰিব।
সেইটো ইনফেক্ট আমি থাকিবনে নাই সেইটো সময়ত, দেট ইজ দ্য মেইন কুৱেশ্যন। বিকজ এইটোৱে এতিয়ালৈকে ইমান ডাঙৰ কলাবৰেশ্যন গমেই পাইছে, কাৰণ বিকজ দেৰ আৰ চ' মেনি ফাণ্ডিং, সেই ফাণ্ডিংটোৰ কাৰণে আমি কৰিব নোৱাৰো। ইনফেক্ট আপোনালোকে হয়তো এটা এক্সিলাৰেটৰ হোৱাৰ কথা চলি আছে। I think,
Cotton University. Yes.
সেইটো যদি হয় ভাল কথা। কলকাতা VCC এটা আছে, কিন্তু যোনটো যদি অসমত যদি এইটো হয়, তেন্তে ইট উইল বি আই থিংক লাৰ্জেষ্ট। চলি আছে এতিয়া, নাজানো। আই থিংক এপইণ্ট কৰা হৈছে ফেকাল্টি, এজন নতুন ফেকাল্টি, এখন জীৱন ছাৰ নেকি নাম তেওঁৰ। তেওঁ চাগে তাৰ মানে মেইন
I think director
মই তেওঁৰ একজন ষ্টুডেণ্টৰ লগত ৰিচেণ্টলি কথা পতা হৈছিল, একচুৱেলি মই ইয়াৰ পৰা যোৱা কৰি আছে, কেনেকৈ কৰি আছে। বাট সেইটোৱে মানে কেতিয়া হ'ব কথাটো খুব মানে, আৰু এটা কথা, there are so many political issues.
Yes.
Political issues এটা ফাৰ্ষ্ট কুৱেশ্যন এটা আহি যায়, পাৰ্টিকুলাৰলি অসমত। চ' আমাৰ এনেই অট'মেটিক ইমান প্ৰব্লেম আছে, তাৰ ওপৰত ইমানখিনি টকা ইয়াত ইনভেষ্ট কৰা ডাঙৰ কুৱেশ্যন। ইণ্ডিয়াত তেনেকুৱা বহুত এক্সপেৰিমেণ্ট আছে, নিউট্ৰিনো এক্সপেৰিমেণ্ট, নিউট্ৰিনোৰ কথা আছিলে, কিন্তু এতিয়া তেওঁলোকে হৈ উঠা নাই। আমি যোনটো কৰিব পাৰো, আমি তেওঁলোকৰ পৰা হেল্প লৈ আমি মেম্বাৰ হ'ব পাৰো, মেম্বাৰ হৈ এটলিষ্ট কৰিব পাৰো। কোনফালে গৈ আছে, এইটো ডাঙৰ কুৱেশ্যন।
And Nihar, I have one question. Your hadron colliders that you were talking. So আমাৰ চাইনাত আমাৰ এটা শুনিছিলো যে আমাৰ এটা লেপটন কলাইডাৰ এটা linear কি কৈছে ILC, I think it was ILC.
আমাৰ অলৰেডি আছে লেপটন, মানে লেপটন আৰু মিউন, লেপটন। তো ইলেক্ট্ৰন কলাইডাৰ আই থিংক এটা বনাই আছে, ইলেক্ট্ৰন প্ৰজেকশ্যন কলাইডাৰ। আৰু এনেও আমাৰ আদাৰ আই থিংক এক্সিলাৰেট কৰা হয়। তো আই থিংক ইউএছটো এটা আছে, বাট চাইনা এণ্ড আই থিংক এটা বনাই আছে collider.
Yes, electron positron collider. Yes.
China, because they are great in technology, and our field, particularly our CMS, Chinese people ভর্তি মানে এতিয়া অসমৰ পৰা বহুত জনে জয়েন কৰিছে, মানে কোলাবৰেচন অফ ডিফাৰেন্ট ইনষ্টিটিউটত। city কৰাই কিছুমান এতিয়া different IIT indoor আৰু I think indoor আছে আমাৰ collaboration তাতে join কৰিছো কিছুমান আছে ভালে কিছুমান আছে লাহে আমাৰ স্কিলটো বাঢ়িছে
নাই অসমৰ মানুহ আছে লগ
উম,
পাইছো
উম।
DA কনফাৰেন্সত
হা exactly মই দিয়ে
the
যাব
community
নোৱাৰিলো
is increasing, yes.
exactly if you have because মই বনাইছো তোমালোকৰ কাৰণে without
I
because
think particle physics মানে even if we try to
মই
explain it
গম পাইছো
in graduation level is quite difficult. বেলেগ ফিজিক্সৰ সাবজেক্ট বিলাক পাৰি অকমান বাট পাৰ্টিকেল ফিজিক্সটো মানে
exactly
বহুত ডিফিকাল্ট হৈ
আমিও
যায়
মাষ্টাৰ ডিগ্ৰী গৈয়ে ফাৰ্ষ্ট পাইছিলো ন
yes
পৰা
yes
অলপ
হুম
মাষ্টাৰ ডিগ্ৰীতে
exactly
পোৱা যায়
আন্ডাৰ গ্ৰেজুৱেট ষ্টুডেণ্টৰ কাৰণে মানে অকমান
উম।
বেছি হেৰি হৈ যায়
সেইকাৰণে মই stuff
yeah
just more spend কৰিছো just to get the
yeah it is fine yes
so I hope
they will know the at least the terminologies and they will get the information code ki hoye ase that is I think sufficient get into the details of physics part but I think this is a good beginning
yeah.
yeah okay then we can close this session if no one has any more question do you have any question anyone
Anyway,
okay
if you সেইটো কৰিব পাৰা প্ৰব্লেম নাই ভাবিছো মই ইমেইল
yes
আইডি দিয়া যদি কেতিয়াবা not now in future
yes let's someone has any question I saw a raised hand you can ask if you have
Hello, sir. I'm Mr. Trinoyan Saikia from North Lakhimpur College.
yeah
nice
I am currently pursuing high energy physics in masters.
okay
Sir, I have a question that do you think it is possible that we can use these colliders for energy generation for our public use?
yes it is producing energy no doubt okay now your question is whether we can use that energy
Exactly, sir.
electricity or some kind of stuff. I think it is, yes, it is possible. It is possible because why not? Because amount of energy, we just need to extract that energy in some form. And if you go to the slide, I have given the source also. The source is the breast. Okay. So if
okay
you interested, so in that source, just there a link, you can see there from the energy point of view going on. From তো এইটো obviously এইটো possible মানে কিন্তু কিমানখিনি হৈছে এতিয়ালৈকে I'm not sure it is possible
but my point is that you are already using a tremendous amount of particles so
Yes, sir. Exactly.
anyway these whatever energy is released in terms of the kinetic energy of these jets so will it be greater than whatever energy you are using I don't think so I mean
okay now you
so,
are talking about the efficiency whether it is to
so
get the
efficiency
energy
will be always
yeah
yeah I
so
in my opinion maybe
yeah
yeah
it needs actually the power বহু power তাতে ই হৈছে মানে ইনফ্যাক্ট মই এটা তোমাক ফান ফ্যাক্ট কওঁ তো এই স্টার্ট হয়েছে তাতে বহুতবার জাস্ট স্টপ করা হয়েছে বিকজ পুরো ইউরোপৰ সেইখিনি জেগাৰ যোনটো পাৱাৰ দৰকাৰ সেই পাৱাৰটো মানে এনাফ নাছিলে কামটো স্টপ কৰা হৈছে সো ইন দ্যাট ৱে মানে আমাৰ পাৱাৰৰ ফালৰ পৰা কিন্তু যোনটো জেনাৰেট হয় তাতে সেই এনাৰ্জিটো চাগে in some form of other energy convert করা আমি কৰিব পাৰো কিন্তু যদি efficient, maybe not. সেইকাৰণে চাগে ই হোৱা নাই তেওঁলোকে ইমান হয়তো ডেভেলপ হ'ব মানে টেকনলজি সেইটো চোৱা নাই সেইটো হৈছে যোনটো কম্পিউটিং চিষ্টেম যোনটো এইটো কোৱা তুমি টেকনলজি যদি কোৱা হয় সেইটো বেছি হৈ আছে বিকজ কম্পিউটাৰাইজ তেওঁলোকে কি কৰি আছে কেনেকৈ আমি মোৰ এণ্ড মোৰ কম্পিউটাৰ ইয়ত যাব পাৰো সেইটো বেছি টেকনলজি AI like AI technology use কৰা গৈ আছে সেইটো ইউজ কৰা হ'ব so মোৰ ডিজিটেল হৈ আছে এইটো চাগে হৈ আছে কিন্তু ইমান মানে ডাঙৰ পৰিমাণে হোৱা নাই কিন্তু LEC এড্ৰেছ কৰিব পৰা নাই কিন্তু মেডিকেল লাইক ৰিলেটেড সেইটো দুটা সেক্টৰ বেছিকে হৈ আছে LEC যোনটো আৰু এনভাইৰনমেন্টেল পাৰ্সপেক্টিভৰ পৰা তুমি বুজিছা এনভাইৰনমেন্টেলৰ পৰা আই থিংক এতিয়ালৈকে ডাইৰেক্ট এপ্লিকেশ্যন হোৱা নাই মেবি তাৰে টেকনলজিটো আছে সেইটো হৈ আছে
Any more question? So any last question? If not, okay. Thank you, Nihar.
Thank you,
Nihar.
Devendra.
Yeah.
Thank you all. So we'll see some person in some other days. Thank you.
Yes, sure. Let me know when you come to Abhayapuri.
একদম নিশ্চয়
Yes. So Dipsika, you want to say any comment, any question?
No, actually, I want to thank the speaker.
Yeah.
Your talk will definitely students and also students from our other institutes. So thank you.
Yeah. No, সঁচাকে মানে like so তেনেকুৱা I was like very excited to have this kind of lectures আৰু এতিয়াৰ ডেটত অনলাইন হোৱাৰ কাৰণে বহুত সুবিধা হৈছে I wish new series of physics and if it is I'm not sure if you make it I'm not sure whether it is but will be YouTube or Zai it will be very nice like,
Yes, we have recorded and it will be available in our channel, so it will be available there. Yeah.
It's always great pleasure মই যদি Abhayapuri College পঢ়া নাই but yeah
Just when you come to Abhayapuri.
Obviously.
Okay, then thank you.
Bye.
Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you.